I want to start with protein geometry. So if we're going to do calculations on protein structures and designs of protein structures, we have to start with the coordinates of the protein and where the protein is in space. So there's two ways to define the coordinates of a protein. One is we can use Cartesian coordinates. So everybody knows those. That looks like a bunch of triplets of x, y, and z. So we have x, y, and z coordinates. We can do that for every single atom. So when you did PyMol on Monday, you looked at those on the screen. Inside the computer, it has x, y, and z coordinates. So if you look at the PDB file, there's x, y, and z coordinates for every atom, and that's where we start with the visualization. So that's nice, and it puts the points in space, but what really matters is where those atoms are relative to the other atoms. And so what we really want to look at is an internal coordinate representation of the protein. So we also have an internal coordinate space. Where we're going to look at a set of lengths of bond distances between atoms for atoms that are bonded together. Angles, bond angles, and torsion angles. So these are bond lengths. Bond angles and torsion angles, or dihedrals we call these. All right, so I basically want to go through some of the calculations that we can do with those. So number one, we'll start with bond length. So if we have two atoms, A and B, put them at three coordinates in space, x, y, z, and then we say they're bound together. Bond. So if we say if we had coordinates for those, x, y, z for A and x, y, z for B, we could represent a position of A in space with a vector A and the position of B in space with a vector B. And then all we want to know is the line AB and the magnitude of that line, right? So that's pretty straightforward vector calculus. So we really want to take the change in the x coordinates and square it, and the change in the y coordinates and square it, and the change in the z coordinates and square it, and then the simple hypotenuse of that triangle of that three-dimensional coordinates, we would get out the length between those two points. Okay, similarly, if we were given where A is in space and you knew how long the bond was and you knew what direction it was going in, all you need to do is add that length onto the coordinates. So if we wanted to place the atom B, we could start wherever atom A is, and then we could add length to it if we knew the length of the bond, and then we just have to go in the direction of AB. So I'm going to use a hat to indicate a unit, let's say a unit long vector. So where AB hat equals AB vector over AB vector norm. So we need to know the direction, which way this is going to go, but then we can take that direction and multiply it by some length L and add that to the coordinates. We get the new coordinates of point B, right? So this is pretty straightforward. So any questions about how we're representing these as coordinates or vectors? The bond lengths are fairly trivial. The bond angles aren't too bad. So at a bond angle, we would have three atoms, A bound to B, bound to C. And what we want to know is what's the angle theta spanned by that bond, by those 3 points. So if I give you the 3 coordinates, how do we find theta? You remember the geometry relation that we can use for this? Anybody? They were quiet, camera shy, or we forgot. How many people remember?
It was a long time.
What do you think, Kushan?
Like the dot product is cosine.
Yeah, so
times the length or something.
go ahead.
I don't remember exactly.
Yeah, so there's a relationship between cosines and dot products, right? So if we have 2 vectors, and let's say we call this vector B and vector C, then B dotted with C is the norm of B, the norm of C times cosine of theta between them. And basically we can turn this around to do the same thing with this here. So in this case we have 2 vectors. We have vector A to B, vector B to C. So we can write cosine of theta equals AB dotted with BC divided by the norm of AB times the norm of BC. All I've done is convert this relationship by pulling the norms over to the left. The one trick is here these 2 vectors are together, whereas in this case we're putting AB and BC end to end, so this formula would really be for this complement here. So to change that, the cosine of the complement is going to be the opposite of the cosine of the angle, so we want a negative sign there. I could use this notation where I look at unit vectors. I could call this minus AB hat dotted with BC hat. So if we take the 2 unit vectors, we can just dot the 2 unit vectors together and take the opposite. We might be given the location of A and B, a length of a bond L to get to C, and a bond angle theta. And we want to find the coordinates of C. So how do we do that? Basically we did this before with just a bond length. If we just had a bond length here, we take B, we take this direction, and we add L to it times that direction. So C we can place at B plus length times, and now we need this direction. So if we know these 2 points and we know the angle, well, what we can do is project this down here. We know part of this is in the AB direction, and part of this is normal to the AB direction. So that's basically what we're going to add together. So we're going to take the AB direction part, and we're going to multiply that by cosine of theta, because cosine of theta will tell us that part of the triangle. Let's see, and then we're going to add P times sine theta, and then P is going to be this direction, this perpendicular direction here. The direction is this way, and this way is the AB direction. So how do we get P? Well, for P, we need to, well, we're going to have to know something about the 3-dimensional geometry of which way to twist this around. So P, well, if we, let's see, so basically we arbitrarily need to choose the plane of A, B, and C. So if we're given, say, n hat is the normal to the board or your paper, then we can say P hat is going to be BA hat crossed with N, and we have P going in this direction. then there's one other piece that I'm missing here is cosine theta. Theta is this angle, not this angle, so I actually need the complement there, so I'm missing a sign there. So there's my formula to put C in place. Given the length of A, given the length, and given theta, put that together. Any questions? Yeah.
Yeah, I think it would be AB hat, right?
Yes, you're totally right. And let's do P hat also, just to emphasize how that goes together. Thank you. Yeah, that's the unit vector in the AB direction, and the unit vector in the P direction. Dihedrals, torsion angles. So here we have 4 points now, A, B, C, and D, so 4 atoms. And we're going to be twisting around the BC bond. So we're rotating or twisting around that bond. If we look, so this is looking in the plane of A, B, and C, and as we rotate, D is going to come out of the board and around back into the board. If we instead look down, let's do this way. If we look down this way, we're looking at A and then B and C. We would have A, and then down below we'd see B, and then back behind that would be C, and then this would come out and we'd see D here, and we'd have this rotation angle here. That would be the torsion angle. This torsion angle we're going to call chi, which is what we conventionally use for side chains of proteins. On the backbone, it's phi sine omega, but in general, a torsion angle we call chi. If it's 0 degrees, we'll call this occluded. So we can see in the models here, we can look down the model, and if we rotate this around at 0 degrees, they're occluded, so D and A are right behind each other. You wouldn't see them. If we go clockwise, that's going to be positive. By convention. What happens if I messed up A and D and I look down the other direction? So let's see, if I go plus 45 degrees, plus 45 degrees, and I turn it around, now what do we have? I'm going to pass this around. The answer is you should see the same thing depending on if I push the back one to the right, I turn it around, and push the back one to the right, it's the same thing. So it's invariant depending which way you look. So let me pass this around. You can play around and look at the angles. Yeah, let's see. We also need to define which atoms are going to do this. I think in the PyMol workshop we had this, we measured some of these dihedrals, and I got a few questions about chi1, which atom do I use to define this? So in general, atoms are defined along the N to C order. So we usually follow along from the N terminus to the C terminus of the protein, and we follow atoms of highest precedence, which means we look at the heavy atoms before we look at the hydrogens, so we don't worry about the hydrogens before that. Instead, we go down the backbone first, and then the heavy atoms along the side, or the longer chains if we're going out a branch side chain like an isoleucine. All right, so if we're looking at a peptide, we're looking at angle. I always get this wrong, which one is which. We want the one before is the omega angle, but it might be wrong, it might be over there. So if we're looking at psi, the 4 atoms are going to be the C from the residue before, so your residues are defined from N to the CO. So we'll call this residue I, this residue I minus 1, this residue I plus 1 as long as the chain as we number the residues. So we'll have the C atom from I minus 1, and the N, and the C alpha, and then the C from the carbonyl. That'll define our phi. For psi, it'll be, we'll just shift that register down, so it'll be NCCON. So N, C, alpha, C from the carbonyl, and N for residue I plus 1. I'm not going to write omega because I can't remember if omega goes before or after. I can't remember which is the convention. I'll write chi 1. We do chi 1. That's the angle coming off the side chain. And so we'll have N C alpha, C beta, C gamma, C alpha, C beta, C gamma. So I had a question on Monday. Somebody asked, well, why can't I just go from the CO, the carbonyl carbon back? What happened when we did that? Was the number the same, different?
Yeah.
It's not the same, I'll give you that. How is it related?
With the complement?
Not the complement.
The opposite.
So remember, this has this also has a proton. Actually, I'm not going to get my stereochemistry wrong here. So there's a proton on there. So if you look down chi 1 from C beta, if you look down chi 1, there's 3 atoms coming out there. So if we take those 3 atoms and we rotate them, we rotate it to look at the next atom around from the top. How many degrees in general offset is the N and the H and the C as you're looking down from the top? 120. Right? If this is a tetrahedral atom and we project it into the plane, there's 3 there, and we'll divide it the circle that way. So yeah, if we did it backwards, it's roughly plus or minus 120 degrees. If it's an ideal tetrahedron, it should be 120 degrees, but usually they're off just a little bit, so they're within a degree or 2. There's a couple different ways to do the math. The one that's most intuitive to me, but takes longer to do the formulas, one of the issues is that if you, let's see if we take A, B, C, and D. So you're rotating D around and A around, so you might just think you could take and if you look down that model, you see the angle between these, you might just think you'd take the dot product between those 2 angles, but the problem is these guys are stretching out forward and back from the bond, so if we wanted to just do a dot product between these 2 AB and CD, we'd first need to flatten them out, essentially what your eye does if you're looking at it from the end. So you need to find the planes that are normal and then project A prime here and D prime here. And then if you turned it and looked at it, then you'd be looking at that diagram. A, B, C, and D, and then we could directly observe that angle, and we could again use that cosine formula. So for that method, we could write BA prime. We'd have to derive this vector. To do that, I want to get rid of the component that goes in the direction of BC. So to do that, I would take BA, this vector here, vector from B to A, and I would want to subtract this. Well, this component is the component of BA that's in the same direction as BC. So I could do that with a dot product, because a dot product will take a vector and project it down and tell you basically this, this distance here. So if we subtract off of this, BA dotted with the CB direction would tell us the length of this vector in the CB direction. And then if we take that's a scalar, and if we put it back, multiply that by the direction from C to B, then that would bring us, add it back and take out that component. So that's a way to get BA projected into this plane. We can do the same thing with CD. Are you with me still or not with me? Questions? All right, let me see if you're with me. Take 30 seconds and see if you can write the expression for CD prime. How, Elizabeth?
I have CD minus CD dotted with the direction of BC.
Of
B, yeah.
C, okay.
Times the BC direction.
Great. People agree? Maybe disagree? Okay, cool, thanks. Yeah, that's basically it. So we have those two vectors, and then to finish it off, the last step is to use that cosine formula again. So cosine of chi can be now BA prime dotted with CB. Sorry, BA prime, the directional vector, the unit vector, and the CD prime, unit vector. So we dot those two together, and that'll give us cosine of chi. Yes, shall I ask?
What's the difference between CB hat and BC hat? Is it minus sign?
BC goes that way, CB goes that way, exactly, it's a minus sign. Yeah, so actually if I use both of these, and multiply both by -1, they're probably the same. But since we repeat it there, it probably doesn't matter. Okay. Let's see, so that's method 1, that's the projection method. The second method is called the normal method. Not because that one's strange, but because this one involves the normals to planes. So let's draw this in 3D. We can. Here's atom A, B, C, and let's see, to do this right. Let's put A, B, and C are in a plane. So put along this BC vector, this plane that A, B, and C are in, right? Any 3 points form a plane. And then if we rotate out of that torsion angle D, atom D, then we can put, think of this as another plane that B, C, and D form. And then what we want to do is look at the angles between those planes. So those planes, as they rotate and come together, that would bring these two things down to 0 degrees, and as they open up, we would do something flat, and that would be 180 degrees. So we want to look at the angle between these planes. So we can do that by just want to try and draw this right here. So if we look at a normal off of the BCD plane, and we look at a normal off of the ABC plane, call this normal 1, call this normal 2. Then what we want to look at is the angle in between those two normals, and that angle would be not exactly our chi angle, because it's going to be the complement to that, so that would be pi minus the torsion angle chi, where we're using the radial coordinates, or radial degrees. Okay, so that's the normal method. So to do that, we need expressions for the normal. So how do we get the normal to a plane defined by 3 points. So for that, we can take AB vector and BC vector. If we take the cross product, AB cross BC, we'll get a normal coming out of the plane. So a cross product will give us a normal. So we take AB cross with BC. That's going to have, depending on the length of those bonds, that won't necessarily be a unit vector. We want the unit normal. We're going to divide out by the magnitude of AB and the magnitude of BC to get normal 1. Normal 2 then would be very similar, and we would take BC cross with CD, divide that by BC, CD. Normals. Does everybody know the cross product? Should I go through a definition of a cross product? Anybody need a cross product definition? Okay, we can check Wikipedia if you need, I guess. Let's see. So yeah, let's see, everybody's doing right-hand rules. What do we see about the signs? Are we good or are we not good? B, C cross CD is going down, so we're actually the opposite sign here for the way I've drawn this. Yeah, AB, BC is coming out of the board, that's the way I drew it. So then we can write cosine of pi minus chi. Cosine of that angle should be the dot product between normal 1 and normal 2. The cosine of the complement is the opposite of the cosine of the angle, so we can write that as cosine of chi is minus n1 dotted with n2. We can plug these definitions in. N1 is AB cross BC over AB BC magnitudes dotted with BC cross CD over BC CD magnitudes. Shoot, and we could have written those as unit vectors. So we could write AB hat cross BC hat dotted with BC hat cross CD hat. So that's probably our simplest version of the formula. All right. Any questions about either of these methods to go from the coordinates to the torsion angles? So on homework 1, I've asked you to do some of these calculations. You can get coordinates out of the PDB file, plug in some formulas and get equations, get the internal angles and bond lengths. And I also thought this would be a useful exercise to get on board with Python, so you can write some Python to crunch these numbers for you, because after this week you probably don't want to see these formulas too much anymore. Once you've got it coded up, you can let the code do it for you. Okay, so to go back the other direction, to go from torsion angles to coordinates, now it gets a little tricky. So the problem is you've got A, B, and C, and then it rotates out of the board to D, and this could be anywhere in space, and it's kind of arbitrary, so it gets a little bit, we're out flying in space, so it gets a little trickier. So before we go to that formula, I want to make a quick detour and talk about rotations in 3D, because the problem is this can be oriented anywhere, and I can do some math if I choose the coordinate system and get it clean, and then we can rotate it into the position where A, B, and C are. So if we have coordinate system X, Y, and Z, we have some vector A in that coordinate system, and I'm going to rotate it some angle theta to vector b. So this would be a rotation, rotate A by an angle of theta around, in this case, the z-axis. So if I'm looking at this at x, y, and z is coming out of the plane, the z is the axis that we're rotating around. So when we do rotation, we need a rotation axis. To calculate this, b, the new coordinates of b, will be the rotation matrix dotted with vector A. So the rotation matrix is going to be a 3 by 3 matrix. In this case, R is going to be, you could do the math. If you think about A being in the x direction, if I move to B, I'm going to need the cosine and the sine to get the new x and y directions. So cosine theta would give the new x, and actually minus sine theta would give the new, well, sorry, let's go the other way. Cosine theta would give the new x, sine theta would give the new y, and 0 would be the new z. And if I had a vector that was in direction, so these are all going to get, when I multiply this, these would all get multiplied in R, they would get multiplied by the first component of A, or the x coordinate of A. If A had a y coordinate, it's going to rotate around here. The y coordinate, again, you can use sines and cosines. So the new x coordinate would be minus sine theta, and the new y coordinate would be cosine theta, and the new z coordinate again wouldn't change. And then the new z coordinate only depends on the old z coordinate, so that stays as a 1. So this is a rotation matrix for rotating by theta around the z-axis. That rotation matrix will do that for you. Does that make sense from some geometry? So that's one you can visualize. The axis is u. We'll call it u hat, and that's 0, 0, 1. And so it turns out, if you look at this rotation matrix, if we had the x-axis, something on the x-axis, and we rotate it up to here, the new coordinates in the new system are actually going to be cosine theta, sine theta, 0. So these are representing the coordinates of the new system. And it turns out that you can take a vector, and you can multiply by unit vectors E in the x direction, E in the y direction, E in the z direction, where these are the unit vectors, x, y, and z. And if you dot that by x, that's a way to transform from one coordinate system into another. So you take one set of axes and move things into a second set of axes. So all we need to know is the unit vectors in each of the two frames of reference to put them together, or the unit vectors x, y, z, and then in the unit vectors of one coordinate system and the dimensions of the other coordinate system. So let's see. Okay, so that's a rotation. These all rotations are happening around the origin. If we want to do a rotation around a different point, we're going to need to translate to the origin, do this rotation, and then translate back. Shift the frame of reference to rotate around the point. So if we have A, and we'll take B and rotate it to B prime. B prime minus A prime, this vector, B prime minus A is going to be a rotation of B minus A. So if we were centered at A, then the coordinate B, we translated this back to A, we just take the difference between those. And so B prime is just going to be rotation B minus A plus A. So we have to move it, B minus A, we'll move it back to the origin, we rotate it, and then we add A back to push it back to where it goes. Okay. I'm going to skip the general rotation matrix. So this is a formula for rotating around X. You can put X and Y's and Z's together and multiply them together to do that. There's also a formula to take a general axis U and rotate around that general axis. I think I'm going to skip that just for time, but you can look up the general rotation matrix if you need. Torsion space to Cartesian space. And turns out to be fairly computationally efficient. Basically, we're going to be given length, theta, and chi, and we want to place atoms. So if you're going to fold a protein and you want to try lots of different folds, you're going to test out one set of phi size, another set of phi size, and you're going to be moving the protein and flopping it around a lot. So it turns out this calculation is one you have to do a lot of times. So we will spend a little bit of time on making it efficient and easy to do. And this seems to be one of the easiest ways to do it. So step one, choose a simple coordinate system. And place the atoms. And the one that Parsons liked looks like this. So if we do X here, Y, and Z, make sure that the cross product still works. What we're going to do is put B down here on the negative x-axis. We're going to put C here at the origin. So the BC bond is along the x-axis. I want to put A in the xy plane. So straight down there. So A is in the xy plane. So all of these have z coordinate 0. There's A, B, and C. And then what we're going to do is try to place D up above it. So we're basically starting with the 3 atoms. We talked about, we used the length and the angles to place 3 atoms. Now we're going to pretend that they happen to be at this really nice coordinate system where C is at 0, B is at negative x, and A is here. And we want to place D out here. Okay, so how are we going to do that? So let's see. So one easy way to do it is if we know the length and theta and chi, if we just take the length into account, and we take this bond and we keep going, we can put it along the x-axis. So we're going to call that D0. So D0 is going to be L00. That's easy enough to do intuitively. We're just going to go with the length L along the axis. Then I want to do the bond angle. So ABCD should have a bond angle. So if I keep this in the XZ plane, sorry, the XY plane, and pull it over here, I can rotate this down through, let's see, my bond angle here is theta. So that means this angle is going to be pi minus theta. That'll be the complement. And I'm going to call that D1. Okay. So take that L and I'll rotate it back. So D1, and we can kind of do by inspection that. We're going to take vector L, we're going to put it back, and we're going to get minus L cosine theta times L sine theta and 0. So the minus cosine theta is because, again, we've got the complement, so we want the cosine of theta, the cosine of pi minus theta will give us the opposite of the cosine of theta. So the cosine is basically this component of the triangle, and then the sine is basically that component of the triangle to that rotation. Okay, still with me? So then the last thing we need to do now is then take the torsion angle and rotate around the torsion angle chi. And when we do that, we're basically going to be taking this d1 and swinging it in a circle around the x-axis. So making a circle like that. And as we rotate chi, if we rotate through, say, some chi angles, we'll end up putting d here. Here's d2. And now again, we'll just take these components and we're doing a rotation around the x-axis, so we use those rotating around the axis formulas where we're just going to get sines and cosines out. So we get d2. Sines and cosines, we're going to start with these that already have the sines and cosines of theta, so we get minus L cosine theta, rotating around the x-axis, so the x-axis, the x-coordinate doesn't change. But then y becomes L sine theta. And as we rotate, we're going to use cosine chi. So if we don't rotate at all, cosine chi is 1. If we rotate 90 degrees, it goes away completely. And then the z-coordinate is L sine theta. And we're going to have sine chi. So again, if we didn't rotate, it would be 0. And then as we rotate to 90 degrees, it becomes 1, and then it cycles around again. All right, so we're just taking that coordinate and rotating it around. Any questions? You still with me? Okay. All right, so that's step 1, is we took a simple coordinate system and we put the atoms in a simple coordinate system for placing D. All right. Now step 2 is, it's probably not the case that our C alpha atom was at the origin. It's probably somewhere out in space, so we're going to have to take that C alpha and going back along the backbone and place things where they go. So step 2 is move to correct place in space. Which basically looks like this. The final placement of D is going to be some rotation matrix M times D2. Take that position of D2 that we had, and we'll add to it C. So somewhere we're going to have to start with C where it actually is in space. We're going to take D2, which is in this local coordinate system around C, and we're going to rotate it by this matrix M that gets the rotation, puts it in the right orientation wherever this protein is. Okay, so M, and all we need is M. So M is actually not as complicated as it looks. So basically, we have two coordinate systems. If we picture these x, y, z axes is one frame of reference, but these atoms A, B, and C are actually rotated somewhere out in space. What we want to do is rotate back to these coordinates. So what we want to look at is this x, y, z coordinate system where it is out in space. So if we have a protein out in space and we identify what those x, y, and z unit vectors are, what these directions are, then we can just change from that particular coordinate system to this one that's oriented this way. So that's the orientation we need. To do that, all I need to know is where these unit vectors are relative to these atoms. So I need to know where is this x-axis relative to A, B, and C. And, well, that's simply in the BC direction. That's the x direction. The y, well, A is in the xy plane, so to get y, I want the plane where this is. It's not necessarily useful, but z is perpendicular to that, so I can get the cross product of A, B, and BC will get me z. And then the cross product of those two will get me A, so let's integrate those down. So the rotation matrix, I'll write it down simply first. So BC, the unit direction in BC is the x-axis. The y-axis, let's skip for a second. The z-axis is a normal. It's normal between A, B, and BC. AB cross BC. And then the third direction is just the cross product between those, so we take the normal, we cross it with BC. So the normal direction here, we cross it with BC, and we'll get the Y direction out of there. Okay. All right, so this is what used to be our X, this is what used to be our Y, and this is what used to be our Z in our simple coordinate system. Okay. Any questions about that? Got a lot of notation, went a little fast, and then it ends up. Maybe other questions? Still with me? Yeah.
So, I asked you a question about this section actually.
Yeah.
You said that something was periodic, and that's why you have the cosine and the sine.
Yeah.
Can you explain that a little bit?
Yeah.
Periodic?
So as I rotate around the XY coordinates,
Yeah.
I'm going to rotate back to where they started. So that this is the sine and cosine we're doing. If this is X and this is Y, as I rotate around, those are going to go, values will go up and down, up and down. Designing a protein or predicting the structure of a protein, there are two big problems. The first problem is there's a lot of conformational space that a protein can flop around in, and there's a lot of sequence space that we can try because there's 20 different amino acids at every site. So this amount of space we have to search through is huge. So the first big problem we're going to attack in the class is called the search problem. How do we search through all that space? Then if we could search through all that space, it leads us to the second problem. Let's say you can enumerate all of the conformations of a piece of spaghetti, or you could take a shape and you could put all of the different sequences of amino acids on it. How do you tell which is the right one? That's the second major challenge, and the answer is you're looking for some kind of energy function or some kind of scoring function. If you're folding a protein, you're looking for the energy that's going to minimize the conformation of the protein, right? If you're looking in sequence space, it might be the minimal energy. It may be something about a minimal fitness in a sequence space if you're doing evolution through the genome. But it could also be analogous. There are some relations to the thermodynamics. In any case, what we're looking for is we need to know something. When we put the coordinates of the protein together, we then need to say what is the energy of this set of coordinates. Molecular energies and forces. And again, this will be a theme of the whole semester: is what is the energy of that protein, and do we have the right energy? So this is a very fundamental scientific problem. It's critical for protein structure prediction and design. And another thing I want to say up front is that this is not a solved problem. We know something about the energy of a protein and what's a higher energy state and what's a lower energy state, but we do not have yet nature's energy function to be able to say from these set of coordinates this is the energy in kcals per mole to 8 decimal places. We just don't have it. We're still learning how to do that. We're still trying to figure out that model. So this is only captured imperfectly by models. So I want to talk now the rest of this lecture and probably a bit of the lecture next week about models for energies. And again, all of these are approximations to nature's energy function, which is something we're still trying to figure out. So yeah, so we talk about this in my lab with current research projects. We'll talk about over the next couple, this lecture and the next lecture, about kind of the starting point energy function, but then we'll talk about variations in it as we go through the semester of different things people have tried and what works better and what works worse and what makes more sense physically and less sense physically. Because it's an open question, again, often in the lab we look at a model and go, why does the computer think this is the low energy structure when we know it's this one by experiment? what's wrong in the computer. We look at it, we try to debate, we talk about it. So we're still really searching for this energy function. So along that lines, your opinions on this are important. If you can see and find things where the computer's not capturing what the energy really should be, your opinions will be valuable. So before we go further, I want you to make me a list of, if you were to write down the energy function of a protein, what would you put in it? What are all the different contributions for the energies that go into the energy of a protein? So make a list, get in it with your partners again, do this in groups of 2 at least, and go ahead and make a list of all of the energies and forces that should contribute to protein structure. Go ahead, I'll give you like 2 minutes. Why don't you start us off then, Matt? There's no wrong answers here today because, again, I know the answer we have in Rosetta is wrong. So it's a matter of correcting it and getting things together. So it's just a degree of how wrong. So, okay, go ahead. What do you have?
So we started with the electrostatics.
Electrostatics, great. Definitely a driver of protein structure. What else?
Oh, van der Waals.
Van der Waals?
So we actually differentiated that between molecular and macromolecular van der Waals.
Molecular van der Waals forces and macromolecular van der Waals forces. Okay. So you have a different perspective than I've, which is probably good. I don't know. What do you mean by that?
So if you have so van der Waals is like instantaneous dipole rotation, right? So you can have 2 atoms interacting with each other. That's like a molecular, but when they interact with each other, they influence each other, and then so they change the way they interact with other van der Waals interactions. So you can have like, sort of like the sum, if you have a bunch of things interacting closely together, then they will act like one big object that has a different property.
Cool, okay, hang on to those thoughts, and we'll circle around to those as we go through these. Why don't we shift to you guys? Do you have a couple on this that are on your list that are these 2?
Yeah, but do you think thermal energy is like a big part in?
Thermo. So thermo basically means energy. Thermodynamics is the energy or the flow of energy. So
like temperature.
Temperature.
So like.
So temperature certainly affects proteins. I would call it a thermodynamic variable, not necessarily an energy or force.
And
hydrostatic. Hydrostatic. Meaning like pressure. Okay. Okay.
Then like chemical energy, like possible interactions, releasing certain energy.
Chemical. Okay, so we got to define these words maybe a little bit
Yeah.
better. But okay, other groups.
Entropy.
Joliasco. Entropy. So I'm going to write that next to temperature. Why am I going to write that next to temperature?
K2.
It's a function of temperature.
Right, free energy, H minus Ts. Temperature scales entropy. So I'm going to put that here. Temperature is primarily going to mess around with entropy. Okay. Yeah, what else? Yeah, so entropy is definitely going to do it. Yeah?
Hydrogen bonding and the hydrophobic effect.
Absolutely. Hydrogen bonding. Thank you. Hydrogen bonding affects protein energies and the hydrophobic effect, whatever that means, right? Okay.
I was thinking of the environment that molecule is in. So for example, if it's oxidative, then maybe the cysteines can form bonds.
Sure. Oxidation state. Yeah, so let's see. This kind of goes more in lines with the thermodynamic conditions: chemical potential, temperature, pressure, oxidation state. The chemical basically goes kind of on there. So I wouldn't necessarily call that a force, but it's certainly going to affect protein structure. It's a variable. Yeah. Others on your list, Matt?
Adsorbed molecules, like ions or water.
Presence of ions, water. Again, not a force or an energy, but certainly a contributing factor. Yes?
And then depletion forces?
Depletion
Is that
forces.
something?
So when things come together and there's a vacuum and You can't get enough solute molecules around that, and it's going to bring things together. Is that what you mean by depletion forces? Yeah, so that can play a role. Yeah, so anything out of colloid science or molecular science could go into this. So that's a pretty good list. Ultimately, we start at the lowest level. We could look at quantum mechanics. So ultimately, the fundamental first principles approach is we'd go back to the quantum mechanics, and we would solve what equation for quantum? Schrodinger's equation. What's Schrodinger's equation? We remember H psi equals E psi. So we use the wave equation, we have a Hamiltonian, we have energy levels, and I think to the best of my knowledge, that would give us the right answer for what the low energy configuration is for a protein. There are a few reasons this is difficult, right? So proteins are large. Quantum we're only able to do on small molecular systems or tens of atoms now, so this is a difficult calculation for us to do. Let's see what else goes here. H. So the Hamiltonian is a function of momentum and position. We basically get a kinetic energy based on the momentum plus a potential energy based on the position. And so we do have methods, ab initio quantum mechanics methods, where we can simulate this equation, try to solve for the wave equation, have different ways of representing superpositions of the wave equation and evolving to get solutions, and those approaches are coming along. But at the moment, we can't do this for a whole protein in a solvent with ions and water and oxidation states and hydrophobic effect and everything else going on. So in the absence of that, we go up to the next length scale. And the next length scale is called molecular mechanics. And in molecular mechanics, we assume that these quantum pieces can come together basically into these molecular forces that you've learned about in chemistry class and thermodynamics class. And what we're going to assume is that we have additivity or separability between different types of forces. So we're basically going to take this list of forces that you have and whittle them down and try to make a set of energies that we can add together. So we can add van der Waals and electrostatics. They're different things. Hydrogen bonding, we can add that, but is that different or is that the same? So a question with molecular mechanics is what's the same and what's different, which of these pieces we can add together. And that's where it starts to become a little bit of an art. In quantum mechanics, it's all in that one wave equation. It's all unified. Physics loves to unify things into a single equation. In chemistry, it's messier. Hydrogen bonding, hydrophobic effect are related, right? Entropy is related to these pieces. They're both related to electrostatics. So how do we add these things together? It becomes a little more subtle. All right, so for example, we could say the energy equals the energy of van der Waals plus energy of hydrogen bonding plus energy of electrostatics. That would be one thing you could do in a molecular mechanics type approach. The standard molecular mechanics, or MD, MD is molecular dynamics, which is a standard technique where you're following the dynamics of a molecule through time by looking at the forces and using Newton's equation. So MD programs are CHARM and AMBER and GROMACS and NAMD, and there's several others. So these approaches, the standard energy function decomposes like this. We take the energy is the local energies plus the non-local. And by local, we mean bonded terms between atoms that are bound together by chemical bonds. And by non-local, these are sometimes called the non-bonded terms, things that are long distance across the protein that are interacting with each other. And then if that gets further broken down, let's see, so the local is, so you can look at each bond, and we can sum over each of the bonds. We can add each of the angles and have an angle term. And we can sum over each of the torsions, torsional energy. Okay, so we separate out the bond length, the bond angle, and the bond torsion. That's the energy in each one of those. For the non-bonded, we sum over all non-bonded pairs of atoms. We have some energy between atom I and atom J, so non-bonded pairs Ij, atom I, atom J. And we can add a sum over non-bonded triplets of atoms, Ijk. That's the term Ijk. For 3 atoms together, what kind of energy do they go? So we get to tell these some of these multi-body forces. So these are 2-body, 3-body, and you could consider this energy function going on to 4-body terms and 5-body terms, etc. Local potentials in molecular mechanics, MM force fields. So let's start with a bond. We have A and B. We have some distance between A and B. We were calling it L before. Literature in molecular mechanics likes to call this Rij. Actually, I should call this I, and atom J. In the computer, we iterate I and J through all the pairs. No questions?
So they're basically treating all of the interactions as like additive?
Yeah. Yep. So if I stretch one bond, that's independent from stretching the next bond next to them. It may not be independent if that coordinate has them tied together, but this bond can stretch and that bond can stretch and they're separate. Yeah, so separability is the first assumption between these potentials. Okay, so how much is the energy given the bond length? That's the question. And the standard molecular mechanics looks like this. Energy of a bond is 1/2 sum over all Ij in the set of all bonds. And it's basically looked at as a spring. There's a bond and there's a spring and it's going to vibrate. So we have Kb, which could be particular for the types of atoms Ij. We take Rij, we subtract off some average Rij, so the over bar now is an average value, and we square this. So the energy, like the energy versus Rij, looks like that. And this point here is Rij bar. That would be a minimum energy. The energy would be 0 when the bond length is exactly Rij bar. And as you deviate from that, it goes up quadratically. So the further away you get, the steeper that is. So that's a spring. If you let it go and had a molecular dynamics simulation and just had 2 atoms, they would vibrate. At constant energy, they'd vibrate back and forth. Right? So that's pretty simple. So to do that, we'll need some parameters. We'll need to know what the energy of the bond is. How much energy does it take to stretch a bond? So it turns out 1/2 Kb is about 400 to 500 kilocalories per mole per angstrom squared. And it turns out most bond lengths Rij bar are about 1 to 2 angstroms. So bond lengths, say, that could be 1.4, 1.6 angstroms. And we vibrate around that. I posted an article with some parameters. See an article by Neria, Fisher, and Carplus in 1996, so this is going back a little ways. And they have a table 4 that has all of these bond lengths, all of these KBs. You can just tell that I want the KB between 2 carbons, and you can look this up, or look between carbon and the carbonyl carbon and the carbonyl oxygen, and you can look up that value. And they've tabulated these, and they've tested them against spectroscopic data, thermodynamic data on simple model small molecules. Carplus, you know Carplus, 2 years ago was given the Nobel Prize for work in the computational chemistry area. So, all right, so that's the bond length. There's also the bond angle and the bond torsion. The formula is the same. It's the same thing, except we're going to use the angle and the torsions now. So we're basically looking at a quadratic function again. So energy of a bond angle is 1/2. We'll sum over all triplets, IJK atoms, in the set of angles that are bonded together. We'll have some spring constant K theta, which could be particular to the atom types, IJK. And we'll take theta, IJK, and we'll subtract out some average or most common minimum energy state theta bar. So we now have IJK, and the angle between them is theta, IJK. And if I plotted energy versus theta, it would look exactly the same as this energy versus our plot. It's a quadratic. It goes up steeply as we change this. The magnitude, 1/2 K theta, ranges from 35 to 80 kcals per mole per radian squared this time. And typically, theta bar is often 109 degrees or 120 degrees, depending on if it's sp2 or an sp3 orbital. So then the last one, energy of a torsion angle. All the torsion angles will be 1/2 sum over all the torsions, IJKL. We have a spring constant K chi, specific to the IJKL pair. And this one's a little trickier because the torsions go around in a circle, so a quadratic doesn't work because that's not periodic. So we have a periodic function. So the typical molecular mechanics fields do 1 plus cosine n chi plus delta. And that graph looks like there's energy from 0. Let's see, if we take n equals 3 and delta equals 0, chi is 0, cosine of 1 plus 1 is 2 times kappa, and then this will cycle down and up, and down, up. This would be 60 degrees, 120, 180 degrees, one more time, down and up. 300 degrees. And then at 360, we match back up. So as you rotate it around, we might have very unfavorable, because these are eclipsed, and then that's favorable at 60, unfavorable, favorable at 180, unfavorable, favorable at 300, and back to unfavorable. So that's our typical potential. There'll be different ends and different deltas, depending on the hybridization and such.